Hello class. So this short video is gonna replace what we should have done today in class. Let's talk about exponential function and look at its graphical representation and how do we find an exponential function if you're given the graph. All right. So I encourage you, if you have not watched the video lesson for today, please do watch it, make your own notes, and use this as a supplement to help you to be able to do the worksheets that I've assigned for you to do today. Now, what is an exponential function? So an exponential function is a function which describes how the graph grows rapidly from left to right or decreases rapidly from left to right. If you look at it from an equation point of view, we're going to define an exponential function as f of x equal to a raised to the x. And if you think about this is probably the very first time from your algebra experience that you're seeing a variable that is a power. It's never happened before. So it is unique in its own. And an exponential function has two characteristics. It's got a base and then it's got a power. So the base, which in this case in the black box is a, and we're going to make sure that a is greater than 1. When a is negative, really you cannot see that characteristic of an exponential function that is increasing rapidly or decreasing rapidly. All right. If it is 1, if a is 1, then 1 raised to any power is 1. Now you don't have that characteristics anymore. It's not increasing rapidly or decreasing rapidly. So we really want our a to be greater than 1 if we want the graph to increase rapidly. We'll look at the scenario when it's decreasing rapidly, but if you want it to increase rapidly from left to right, we really want a to be greater than 1. So that's one characteristics. Okay, we don't want a to be 0 too. All right. And then another feature is that it's always going to pass through the y-intercept 0, 1. If you think about the domain which represents all the x values that this function can take, if you look at the graph, it's going from negative infinity all the way to positive infinity. It can take any x value, right? So when we think about the domain, it belongs to all real numbers or negative infinity to positive infinity. And then when you think about the range represents all the possible y values of this graph. So if you think about the graph, you can see that the graph only lives above the x-axis. So all these are possible y values. So we're going to say that y belongs to, well, you can see that it's from 0 to positive infinity. And then you can also see that as you are approaching negative infinity, as the graph goes to negative infinity, it looks like the curve is tapering along the line y equal to x. And we're going to call that feature of an exponential function the horizontal asymptote. So we have a horizontal asymptote, which is a line y equal to 0. So it's a line that the curve gets closer to but does not cross. So when you are drawing an exponential function, these should be part of the ingredient that makes the graph. You should indicate your horizontal asymptotes. You should see the nature of the domain and range of that exponential function, and it should pass through at least the y-intercept, the y-axis. Okay, now let's look at the second graph. So the second graph, it looks like it's decreasing rapidly from left to right. And when that happens, the a has to be between 0 and 1. That means that it's a fraction. All right, if your a is a fraction, then the behavior of that exponential function is going to decrease rapidly from left to right. Again, it's passing through the y-intercept, which is 0, 1. The domain is still the same. It's all possible x values. So negative infinity to positive infinity. If you think about the range, you're looking at all the possible y values. You can clearly see that the graph, the y values lives of that graph lives above the x-axis. So y belongs to 0 to infinity. And then you can also see that it has this line again, which is the horizontal asymptote, is a line that the curve gets closer to and closer to. In this case, as you go into positive infinity, it looks like the curve gets approaches what? Approaches as x, let's write it this way. As x approaches positive infinity, y approaches what? 0. So we can talk about the horizontal asymptote over here being y equal to 0. Again, an asymptote is an equation, so don't just write 0. It's y equal to 0. So these are some two classic features of an exponential function. We have an increasing one where a is greater than 1, and we have a decreasing function, which is when a is between 0 and 1. So you can easily see how transformation plays a role with exponential function, because I can move the curve up and down, left and right, stretch and shrink. So because of that feature, we need to come up with a general formula other than a to the x. Because when I move, I need to show that, okay, I'm adding a plus c to the function if I'm going to move to the right. If I want to do minus c, I got to show that I'm moving it to the left. So because of that, we're going to come up with this generic form for an exponential function. And what we want to come up with that y, or f of x, is equal to a b to the x plus c, which, if you look at this equation, built in it is what we call this is your vertical, stretch or shrink. You also have in here your vertical shift. So it could either be plus c or minus c. You also have your base. This is the base. And the base could either be greater than 1 or it could be between 0 and 1. The only thing left is I don't have the shift, but once you see the shift, it will appear, the horizontal shift, it will appear with the x. So this becomes our generic formula that we want to stick to. Like anytime you have an exponential function, if there is no shift, then the function is going to look like just f of x is equal to what? ab to the x. All right. So this definition over here, ab to the x plus c, becomes something useful to us when we're looking at exponential functions. All right. So for your homework, this is what I want you to do. I'm going to go through one example and then you do the other two. I'm going to look at example 1 and then I'm going to let you guys work on the remaining one. So again, I'm looking at my generic formula. So my generic formula is f of x is equal to abx plus c. That's my rule. So I'm looking at this question over here. In question 1, I can clearly see that I have a horizontal asymptote at 0. So for me to solve this problem over here, I can clearly see that I have AB to the x plus 0. So I'm really considering just ab to the x. Now they've given me 2 points on that curve, and there are 2 variables that I need to resolve. I need to know what a is and what b is. So you have enough information to help you figure out what this function would be. So if I pick f and I input in the very first point, which is the x is 0, then this reads as ab to the 0. And that outcome, the y value, is 1. Rules of exponents. So those who've done rules of exponents, b raised to the 0 is equal to 1. So we end up seeing that a is equal to 1. Then what this means is that this exponential function, now we know a is 1 times b to the x. Now my goal is to now resolve b. So I pick the second point and I plug in f of negative 1 is equal to b to the negative 1 is equal to 0.2. Well, that's 1 over b is equal to 2 over 10. So what is b? B is equal to what? B is equal to 5. So this function over here is equal to 5 raised to the x. All right. It's 1 times, but we don't have to write the 1. So we end up with that. So that becomes the exponential function. And it should make sense. You could see that a is greater than 1. So the graph is increasing from left to what? Left to right. It's passing through 0, 1. So I'm feeling good about it that I got the right information about this graph. So for your homework, I want you to come up with the equations for number 2 and number 3. Now, the answers are below. So just giving me the answer doesn't do justice. I want to see how you arrived at your answer. So make sure you show me all your work. The second example is, I'm now going to solve one of these. Again, this is 3 questions. I'm going to do one, and then you're going to do the remaining 2 and turn in your work. Again, the answers are below, so just don't give me the answer. Show me how you arrived at your answer. So let's look at the first example. It says that this is in the form ab to the x. We already know that. Now, by inspection, I clearly see that I have a horizontal asymptote. So I can put that into my equation, which is ab to the x plus 2. That is something I can just put in right there because it's a horizontal, it's a vertical shift rather. Now, there are 2 variables that I need to resolve, a and b, and they give me 2 points. So I can utilize that information to help me figure out what's going on. So I have f of 0 is equal to ab to the 0 plus 2 is equal to 2.5. So I get a plus 2 is equal to 2.5. A is 2.5 minus 2, which is 0.5 or half. All right, so again, b to the 0, anything raised to the power 0 is going to be 1. So that's how b disappeared, and I was left with just a. So now my function reads 1/2 b to the x plus 2. Now I'm going to use a second point, which is f at 1 is 1/2 b to the 1 plus 2 is equal to 4. So what do I get? I get 1/2 b is equal to 2, b is equal to 4. So f of x reads 1/2 times 4 raised to the x. So it looks like we had a vertical shrink, and then the exponential function was what? 4 raised to the x. So we shrank the graph of 4 raised to the x by what? By a factor of 1/2. All right, so go ahead and do example 2 and 3. And again, I said the answers are below here, so just don't copy the answers and give it back to me. Show me all your work. So that is it. You have, I think, 4 questions to work on. Do that and turn in your work online for today's work. All right.